All right, here comes your Nikon P1000 sun test. Let's see what we can see at 93 million miles away. Man, y'all check out this raw power, dude. This thing is strong. You know what's weird? 93 million miles away, huh? This camera, man, this camera don't play them.
Okay, so after viewing that video that we just seen, we can carefully observe the sun, and it becomes fairly apparent that there are distinctive sunspots on the surface of the sun. Now, these sunspots exhibit remarkable motion, and they trace a circular path. The movement of these sunspots move in a clockwise direction. Its center aligned perfectly with the center of the sun itself. So by conducting these observations at various times, we can discern that the sunspot's rotation around the sun's center is consistent and measurable for sure. Now, the pattern of rotation becomes very evident, and it underscores the dynamic nature of the sun's surface itself, just like the moon. Now, over a period of 12 hours, we can quantify the sunspot's rotation around the center of the sun. So to do this, we would calculate the angular displacement, denoted as the symbols delta alpha. That's the triangle with the Greek small lowercase a, called delta alpha. So first, we measure the initial angular position of the sunspot, which we'll call alpha 1 or A1, and the final angular position after the 12 hours, which we will call alpha 2 or A2. So now, in this example, the initial angular position of alpha 1 or A1 is 29 degrees, and the final angular position of alpha 2 or A2 is 133 degrees. So the angular displacement of delta alpha is then calculated by subtracting the initial position from the final position. So now the angular displacement, called delta alpha, is calculated by subtracting alpha 1 from alpha 2. So we have delta alpha equals alpha 2, which is 133 degrees, minus alpha 1, which is 29 degrees, giving us a total of 104 degrees, as displayed in the equation. Now, this measurement, taken from a fixed observational point, highlights the uniformity of the sunspot's rotational movement over the specified time period. And interestingly enough, this rotation mirrors the rotation of the moon around its own center as well, as observed from the Earth. Now, this correlation suggests that a fascinating phenomenological movement will always happen, and we will always view the same hemisphere of the sun, analogous to our consistent view of the moon's near side. In other words, we're always seeing the same face of the sun as well. Those are just orbs up in the sky. When we see the sun and the moon, those orbs up in the sky, those are like orbital portal wormholes, rips in the firmament that we can see. And also, I think it's noteworthy to know that the Nikon P1000 and P100 cameras, those super digital cameras, they're renowned for their exceptional optical zoom capabilities, and they have been discontinued. Keep that in mind. So the development raises question regarding the underlying reasons for this decision. And interestingly enough, this discontinuation coincides with Nikon's recent contractual agreement with NASA that they established around the time of the 2024 eclipse to collaborate on an undisclosed project. Use your imagination why they would do that.